Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question raw and uncut. So before we start today, I finally reached 10 subscribers. So I know it isn't that much, but well, as people say, the first 100 subscribers are always the hardest to get. So really appreciate your support. And honestly, if you have any questions that you want me to do, like any LeetCode questions, or if you want me to explain some algorithms, yeah, just leave a message. I promise I'll do it. And yeah, so let's get back to the question. So so we have longest nice subarray. So it's a medium today. So you're given an array nums. So I'm guessing it will be 100k length. Yeah, and we have positive numbers in there. Yeah. So so we call a subarray of nums nice if the bitwise end of every pair of elements that are in different position in the subarray is equal to 0. So return the length of the longest nice subarray. So a subarray is a contiguous part of an array. Yeah, okay, so um maybe we have moved on. But like from decision problems. But yeah, maybe we are getting to the bitwise operation stuff. So let's see. Uh so subarrays of length 1 are always considered nice. Right. Okay. Because it doesn't have any pair. Right. Um so the first observation we should make is that uh it is when do two numbers, like when does a and b equal 0, where like a and b are numbers. Um so if we look at um if we look at, like, let's say 3 and 8 here. So 3 and 8. So why is that 0? Well, first of all, we should turn it into binary. So we will have 1 and 1. And then so that's 3, right? And then 8 would be 1 0 0 0. We can see that um there aren't any positions where both of them are 1. Because like when you do the AND operation, you want to check, like, let's say for the first digit, right? You want to check whether if both of the binary digits are 1. If it is, you want to like put 1 there, but otherwise you want to put 0. So we definitely need a map, or like some sort of um some sort of like position array to make sure that we don't have we don't have two numbers, like when you turn it into binary, that has the same position to be 1. That's extremely wordy. I'll draw it out. So let's say we have a position array for example 1, maybe. So so what do we have? We have 138, 48, 10. So when we look at 1, so one's binary representation is just 1, right? So we want to store that there is a there is a 1 in the first position, right? If we're counting from the right. So like it will be, you know, you can have a bunch of 0, but doesn't really matter. Like let's say the first position is the rightmost position, and then like so the first position, second, third, fourth, and so on. So we know that like we have a 1 in the first position. So that means if we want to expand the subarray more, we can only add numbers that has the last digit as 0, because we want to check for every pair, right? Well, and when we look at 3, well, obviously it doesn't work because like the first digit is 1, so we just want to cut 1 out. Yeah. So yeah, I think that's how we do the question. Um, in terms of how we are storing the actual word, I think what we should do is we should, like, we don't really need an array. what we need is do you want to use an array actually? I think that would be easier to code out. It will be slower because I think like when I code it out, it will kind of make sense. So like that. Wait, actually, maybe I'll draw it out first. So there are two options, right? So either you can like have an array or like a set or whatever you want. So let's say a set. So we have a set. So when we see one, like we will store the first position there, and when we see three, well we can see that like the first and second position they both have um like a set bit, right? So set bit means like if the bit is one. Uh, so that means we want to remove um like the the leftmost character. So we want to the leftmost number. We want to remove until well like the array is nice again. So that means like we just have to go through one again. We want to remove one, and then so now it works. So we can like add one and two in there, and then like when we get here, um, well like when we get to 8, we can like check that again. Well now like we only have a 4 there, and like I think 48 also works. But like when we get to 10. Looks like this, right? So it has the second position here. Um, so that means it doesn't work, and therefore we have to like remove all the bits that works for 3, and we are guaranteed that we won't have two numbers in the nice array that shares the same position here, right? Because otherwise it would not be a nice subarray. So yeah. Yeah, so that's the first way. The second, probably more performant kind of way, is if you have a number and like you turn on the bits instead. So let's say like for 1 you turn that bit on, and then for 3, you can see that well like it has 1 and 2 in there. So um well like you can just check the bits. Well, it's basically this, but they store in a number. But I'll just use a set because it is just easier to deal with, I think. Uh, yeah. And also another question is like what would be our time complexity? So for a 10 to the power of 9 number, we have around 30 bits. So that means for every number, we have to perform like 30 operations on it. And then we have 100k, so obviously that works. Yeah, so we can get coding now. So we have so what do we want? So we want a set. So let's call it scene. Maybe like set bits. We are doing a 2-pointer kind of thing here as well. And then we want longest nice array. We'll set it as 0. Yeah, so in this case, yeah, I think we can mix we can make this we can make R exclusive again. I really like setting R as exclusive because like whenever we are dealing with ranges, it just somehow becomes cleaner. So yeah, so let's get coding. So for x in nums, wait, no, we should do while. I think while R is less than or equal to length nums, but then we have to like check it in there as well to make sure nothing goes wrong. So yeah, so actually, so at first, like let's say for this, we have both L and R pointing here, right? So we want to add this number in, and then we want to move R over. Yeah, so yeah, okay. So we want to so nums r is the number that we want to deal with at the moment. So we'll call like num equals nums r, and then we can do while num. So to get all the binary positions, what we can do is we can have maybe an index. So we want to start at 0. So this will be the position. Maybe I'll call it pos. Probably makes more sense. So we want to increment the pos, and so if num mod 2, so that means the last bit is a 1. What we want to do is we want to add that into set bit. So pause, and then we look at the next position, right? So that's how you get the actual positions. But then we have one more thing we have to check, which is whether set bits is in the set already. So I'll just do it the slow way, but it definitely wouldn't time out. It's just like more. It's just a higher constant factor. So if num percentage 2 modulo 2, and this is very deeply nested, but whatever. So if set bits, if pause in set bits, so that means we want to remove the leftmost character. So so what we want to do is we want to get the num to remove. So that will be nums L, and so again we do while like num to remove. Oh, why is it so deeply nested? Whatever. Yeah, so again, if we just want to do the same thing, but this time we want to actually remove it from set bits. So so we want to remove so pause remove set at 0. We want to remove that, and then we want to shift the the number to remove. Like we want to shift all the bits 1 to the right, so you get rid of the rightmost bit that we have just looked at. And then pause remove. Want to add 1 to it, and of course here we should not forget about shifting the number over. Yeah, so num remove. Oh wait, this one is just num. Yeah, so we want to do that. Yeah, so we're going to have. Should we? Yeah, I think that should work. So it is going to shift. Wait, actually, yeah, we need to after we have removed all the digits, we need to shift that over, and then yeah, we don't want to add this in yet, I think. So if pause in set bits. I know how I can make this code look nicer. So yeah, right now it's atrocious. But let's put this outside now, for now. The indentation is probably messed up as well, but let's just put it outside for now. So what we can do is, we can have a list of yeah, we can just find all the set bit for the current numbers, for the current number first. So position is equal to that. Num, if num is, well, if num mod 2, we can just do num set bits. Just add position in there, and then of course we want to define that, and we want to move position up. Actually, we should move position either. We should do that. Yeah. So num set bit is going to have all the set bits for num, and then what we want to do is while num set bits. I think the intersection operator is this. Wait, actually intersection should be AND. Yeah, I think it's AND. So we can like just combine the two sets. Like we can like we can check the intersection like in the two sets. And if they have an intersection, that means like there are some positions that got overlapped. That means we have to remove like nums L until this is empty. So what we can do is we have num remove. So this would be the code below, but we can just copy this over. Actually, we don't even need what we have written before. Like this. So num remove, and then we just get rid of that. Oh, we actually don't want that. We want so if num remove, we want set bits remove position. I think that's what we want to do. And then we have position, we add the position. So we want to loop through this until we get there. And after we have gotten there, we want to check the size of L to R. Wait, actually. Yeah, I don't think I need R, right? I just do for ix for I num in enumerate nums. And then we can because like we look at R once anyways, so yeah, we don't need this line at all. We just do that. And then so if we look at the first, like the 0th index number, and L is at 0, well, that means we have like one thing in there, right? So yeah. So what we want to do is after this loop here, almost forgot to increment L as well. So after we have done that, we want to do longest nice array. We'll get the maximum, either the current maximum or I, which is the index we're dealing with, minus L plus 1. So that will give us the current nice array length. So we can do that, and then at the end we can just return longest nice array. I hope this works. Uh-oh. What did I do wrong? Okay, well that's not good. So num set bits add position. Did I forget to increment something? Oh, maybe this doesn't work. Let me print num set bits. Maybe that's not the correct way to do it. Yeah, it's just set the whole way. It's just not what we want. Let me search quickly. So the intersection. I do get the correct thing actually. Oh, I know why. So actually, after we have done this, we have to like we haven't added the num set bits into set bits yet. So that was the issue. So I think union is this num set bits. I think. Hopefully I'm correct. Yeah. Okay. Yeah. So this means like adding all the elements in this set into that set. Yeah, it is quite slow. Yeah, actually, let's look at other people's solutions. So they are using, so temp is 0, L 0. I think they're using like the same method, but just a more efficient way. So result is 0, and its length nums. Yeah, so that works. Wait, they don't even need that actually. So for our num, so that's kind of what I did. While, yeah, so instead of using a set, they're using a number, which is like the second option I talked about, right? And yes, it is a lot faster if you use a num, but a set is a bit easier to logic with. Not the best code though. Yeah, but actually this is quite clean. So what they do is they do the AND operator. Oh, like, wait, this is XOR, right? Oh yeah, if they do XOR, they can just erase I think it erases all the set bits there. I think. Yeah, right. Yeah, so they're kind of doing the exact same thing, but they're using like bitwise operator, which is obviously quicker. But yeah. Uh yeah, so yeah, this question is, I don't think it should have taken that long, but yeah. Thanks for watching, and I'll see you tomorrow. Bye.